All right, if you remember, we have two strategy profiles, pooling strategy profiles. The first one is that the both good and bad firm advertises. The second one is both good and bad firm never or does not advertise. So let's look at the first one. Can this be part of perfect Bayesian equilibrium? Our approach is always the same. Fix those strategies, find the optimal P and Q if you can, and then given those P's and Q's, find the optimal strategies of the second player if you can, and given those strategies, check if those strategies of the first player is best response or not, and then verify requirement 3 and 4 holds. If they all hold at the same time, well, then we can conclude that those strategy profiles and the belief system you generate is a PBE. All right, but we have not yet generated this entire strategy profile. We just started with AA. So let's put A here and A here. That means whenever the consumer observes A, all right, given those strategies, she's gonna say, hey, you know what? My opponent, whether it's a good firm or a bad firm, will advertise. So whenever I see advertisement, I still can't say, this must be coming from a good firm or this must be coming from a bad firm. I cannot be sure. So therefore, what's my risk? I mean, what's my belief that my opponent is a bad firm or a good firm? Well, here we're going to do the Bayesian updating. So P is going to be basically 0.6 times the probability that the good firm, I'm sorry, let me put it this way. 0.6 is the probability that the firm is a good firm, and then 1 is the probability that the good firm will play this strategy advertise, all right, divided by what's the probability that I am actually going to end up in this info set. Well, I may end up in this, so this is times, by the way. I may end up in this info set because the firm is a good firm and it advertises, and because the firm is a bad firm and it also advertises. And actually the probability of this is 1, because the probability that the firm is a good firm is 0.6, and then the probability that it will advertise is 1, and the probability that the firm is a bad firm is 0.4, and the probability that it will advertise is 1. So therefore this is 0.6 divided by 1, so therefore P has to be 0.6. Well, in pooling equilibria, you don't really need to calculate the Bayesian updating. I mean, it doesn't have to be really that sophisticated. Because both firms are going to choose advertise, you will basically carry those probabilities to the P, to this information set, okay? However, we cannot calculate Q because the Q appears in the information set that is off the equilibrium path, and according to requirement 3, we're done. According to requirement 4, Q should be updated according to Bayes' rule whenever it is possible, but here it's not possible because the probability of NA occurring is 0 for both players. So actually the probability that I end up at this decision node info set is 0. I mean, the probability in the denominator is 0. All right, so whatever number you put there, I mean, it's not well defined. I mean, it's not infinite, it's not well defined. All right, so therefore, we cannot calculate Q. But that doesn't mean that Q can be anything. We're gonna come back to that. So at this point, let's leave Q alone, all right? So let's leave Q alone and focus on the things that we already know. What is that? Well, we know that P must be 0.6. And therefore 1 minus P is 0.4. So given these beliefs, what is the optimal strategy for the consumer? Well, the consumer cannot say, I am here for sure, and so I should buy because I'm gonna get one. No, it says, if I buy, all right, well then I'm gonna get 1 with probability 0.6, and then I'm gonna get minus 1 with probability 0.4 because I may be here as well. So playing buy is kind of a risky decision. However, if I don't buy, I will always get 0. So the question is, which one is higher? Well, if you calculate this, you're going to see this is plus 0.2, which is higher than 0. So in expected term, buying is still better in expected term. So you know what? I'm going to buy whenever I see advertisement. Although I cannot distinguish whether this firm is a good firm or bad firm, the probability that the product is good is high enough so that I will still buy the product. That's the consumer's decision. Okay, so we actually calculated that the consumer's strategy, at least part of it, consumer's strategy, let's leave this blank, and this one is buy. Okay, so whenever consumer is in this info set, she's gonna buy it. Here, what is she gonna do? I cannot calculate the payoff of the consumer here without knowing Q, because it depends on Q. If Q is 1, decision is simple, buy it. If Q is 0, it means we're here, the decision is again simple, don't buy it. But if Q is somewhere in between, well, you know what? It can be buy, it can be not buy, depending on the specific value of Q, I'm sorry. So what am I going to do? We'll come to that, but let's leave that. Let's first sort of clear the things that we already know. What are they? AA. What does that mean? Well, remember, we can still check if AA is the best response to the consumer's strategies, although we have a limited information about the consumer's strategy. We only know how the consumer will behave here. We have currently no idea what she's going to do here. But this information alone could be helpful to see if AA is the best response or not. So if it is not, well then you don't really need to worry about the Q and the optimal strategies here. You see what I mean? So let's check that. So given that the consumer will definitely play B, is playing A best response for both firms? Given this limited information, let's look at the good firm. The good firm chooses A, and he knows it's going to get R minus C. Well, if he chooses not A, well, you know what? It may get more than R minus C, or it may get less than R minus C. It depends totally on what the consumer will do here. Okay, so I cannot really conclude if A is the best response or not. Not yet, at least, with this limited information. Okay, let's look at the bad firm. Well, the bad firm is choosing A, and as a result of this, getting R minus C, which is negative. Remember, R is less than C. Okay, so the question is, if the good firm deviates and plays NA, can he get better payoff for sure? Okay, let's look. Well, if the bad firm deviates and play NA, not advertise, well, what he's gonna get depends on the consumer's decision, obviously, but he will either get R or 0. Well, R minus C is less than 0. R minus C is clearly less than R. So what does that mean? That means whatever customer does here, which we still don't know, the bad firm actually prefers to deviate to NA because A is too bad for him. You see that? It's very important. Let me repeat. Whatever the customer does here, the firm is going to get either small r or 0, both of which are higher than R minus C. So that means the bad firm will definitely benefit from deviating and not advertising. And hence, A is not a best response for bad firm. Again, although we don't fully know what the consumer's strategy is, even this partial information was enough to conclude that one type's strategy is not a best response. So you don't really have to calculate the rest of the strategy profiles, P's and Q's. Just leave all the calculations there, because I now realize that we cannot have a P. So we cannot have a pooling perfect Bayesian equilibrium where both good and bad firms advertise. AA. It can never be a part of perfect Bayesian equilibrium strategy profile. That's the conclusion. All right? Okay, so this is second potentially strategy, pooling equilibrium strategies for the good and bad firm, where they both not advertise. All right? Okay, so I put the arrows to not advertise. So this time, the off equilibrium information set is the one on the right. All right? And the on equilibrium is the one on the left. So given all this, the Q, exactly the same calculations that we did here in the P, the Q must be equal to 0.6, all right? Basically, you just carry those probabilities to Q and 1 minus Q. And so what about P? Well, I don't know that yet because it's off the equilibrium path. Requirement 3 says nothing about it. I need to calculate it. I cannot calculate it. Requirement 4 doesn't say anything about the value of P. All right, so there's no restriction about the value of P. Okay, so given this information, can I say what the optimal strategies are here and here? I can say here, but I can't say here because I don't know the value of P. But given that the Q is now 0.6 and this is 0.4, what is the expected payoff? Well, again, the same thing. If the consumer buys, her expected payoff is going to be 1 times 0.6 probability and minus 1 times 0.4 probability. So it's plus 0.2. But if she doesn't buy it, her payoff is certainly 0. So you know what? In expected term, buying is still good. So the consumer will definitely buy it if she does not observe an advertisement. Well, is she going to buy, not buy? I don't know. That depends on, again, P. Well, at least I know part of the consumer's strategy. It's going to be buy and something. I don't know what that thing is yet. Okay, so let's do exactly the same thing we did in the other pooling strategy. Our NA's best response, at least with the limited information we have. Okay, so when the consumer here buys, the good firm, all right, so the good firm, if the good firm is currently not advertising and therefore its payoff is R, but if it advertises, its payoff is going to be either R minus C or minus C. Either R minus C or minus C, both of which are less than R. So you know what? Good firm is already best responding. We can say the good firm is best responding, although we don't know the other part of the consumer's strategy. All right? So the good firm is best responding by playing not advertise. Okay, good. Well, what about here? The bad firm, let me write it here. Bad firm is currently not advertising and then currently getting payoff of R. But if he deviates, what's going to happen? He's going to get, if he advertises, he's going to get either R minus C, which is less than R, or minus C, which is also less than R. So you know what? If the bad firm also deviates, whatever consumer does here doesn't matter, but the firm is actually going to get less payoff. So you know what? Bad firm also best responses by playing not advertise. So you know what? That's very good. Even though, again, I don't know half of the strategy of the consumer, I mean this part, I can say the good and the bad firm are both best responding. All right? So NA is in fact part of a perfect Bayesian equilibrium. All I have to do, given that consumers are buying here. So, however, I have to, so there is a pooling equilibrium here, okay? But I have to complete the rest of the strategies, right? I can't leave it as a blank. And therefore, I have to calculate P. So the question is, what strategy is optimal for what P? That's the only thing that matters. So you don't really need to check if these guys are best responding one another. We already showed NA is the best response to any strategy where consumer is playing B here. All right. So whatever you put here, the firms are best responding. So, but you cannot put anything here. The thing that you put in here, the strategy don't buy or buy, depends on P. So that's very important. So how am I going to complete those strategies therefore? Well, look at the consumer's payoff here. If she buys here, she's going to get 1 with probability P, which we don't know yet what it is. And requirement 3 or 4 puts no restriction on P. Okay? So that means P is going to stay as a free parameter. Right? We're not going to be able to find a specific value for P. That's what I mean. All right, if the consumer plays B, she's going to get 1 with probability P and -1 with probability 1 minus P. However, if she plays don't buy, her payoff is going to be 0 for sure. So the question is, it all boils down whether this guy is higher or lower than 0. Well, so therefore, consumer buys if and only if this payoff, which is equal to, by the way, P minus 1 plus P, I mean 2P minus 1, if and only if 2P minus 1 greater than or equal to 0, right? Whenever it's equal to 0, buying is still a best response. All right, consumer doesn't buy it if and only if 0 is greater than or equal to 2P minus 1. Again, whenever 0 is equal to this, don't buy is still a best response. All right? By the way, there might be, because of these equalities, there will be some mixed strategy, perfect Bayesian equilibrium. But again, we ignore mixed strategies, only focus on pure strategies. All right? So let's just solve this in terms of the value of P. So that means P is greater than or equal to 1/2. And that means P is less than or equal to 1/2. So that's it. I can just bring everything together and write down my strategies. Don't forget, we cannot calculate the value of P because requirement 3 and requirement 4 puts no restriction on P because it's off the equilibrium path, I believe. And so P is going to be a free parameter, and that means we will have many perfect Bayesian equilibrium, pooling strategy perfect Bayesian equilibrium. Okay? And so let me just summarize them. NA, and B, I don't know, let me denote this as a square, okay? And then P, and then Q equal 0.6. So the Q must be 0.6 in all perfect Bayesian equilibrium. It cannot take any other value. So this is a pooling perfect Bayesian equilibrium if and only if, if and only if the square is equal to B. Square, whenever you see square, you should put B, if and only if, or whenever, whenever P is greater than or equal to 1/2. And then the square is in fact equivalent to, let's put it that way, don't buy whenever P is less than or equal to 1/2. Well, what's the value of P? That's the thing, it's a free parameter. So there are infinitely many perfect Bayesian, pooling perfect Bayesian equilibrium in this game, but all of which have the same structure. I'm just summarizing that structure. Okay, I hope that was clear.